Are you saying something?
Hello everyone, good evening.
Good
Yes,
evening.
ma'am. Good evening.
Yeah. So today we'll start with week 11. Okay. So till week 10, we had seen the support vector machine and like ending with at the end in week 10, we had also introduced about what is soft margin SVM. Right. We had just introduced what is soft margin SVM. So now we'll look at it in more detail in this week. And then afterwards, we'll look at two other techniques which are called parking and boosting. So, what was the formulation of what was the primal problem for the soft margin SVM? So, the primal formulation for this was my objective function was 1 upon 2 norm of W square plus some C times sum over epsilon I, where I is varying from 1 to n, and we were minimizing over W and epsilon both. And my constraints were W transpose xi by I plus some epsilon I greater than equal to 1. And this is for all I and for, and we had also seen that the second constraint here would be that epsilon I should be greater than equal to 0. So here C was some kind of hyperparameter, and this was kind of giving you an idea of like how much um, how much bribe like each point was paying to go to the correct side. So this is in a sense also this can also be called a slack variable. So this was our formulation, and what we had seen is like if C was 0, we had come to the conclusion that the amount that each data point will pay to go to the right side, um, and if C was 0 in that case, then bribes did not cost, right? So the bribes did not cost, and we had come to the conclusion that uh, the final solution to this problem would be W is equal to 0, where 0 belong to RT. So this should be the solution in case my C was 0. And if C was infinity, what we had seen is like when C is infinity, it is nothing but the linear separability case. This was the linear separability case, right? Because if C was infinity, this would like the objective function would be infinity, and the only way for us to get the non-trivial solution was when the bribes did not when we did not pay the bribe at all. The data points did not pay the bribe at all. So in that case, it is more like the linear separability condition. So this is where we had stopped in soft margin SVM. So now in this week, we will look at the dual formulation of this problem and see like how these alpha is like what will you get W star to be what is the solution for this soft margin SPM. So we'll look at this problem in this week. So when we so this is the problem, right? This is my primary problem. Now this primal problem, we know that if we use the Lagrangian, like for the this is a constraint optimization problem, and we if we use the Lagrangian, so my this function would become, so now you have the objective function, you have two variables, W and epsilon. So you have two variables, W and epsilon, but apart from this, now you have two constraint also. One is this constraint and one is this constraint. So for each of these constraints, you will get alpha I. So you will have some alpha I, some alpha beta. Let's say you have for two parameters for two constraints. So this objective, this Lagrangian function, now what will it become? So the Lagrangian function, yes, Sudhir.
Ma'am, what is the second condition? C is equal to infinity, then.
C is equal to infinity. So if you look at this objective function over here, this, so what we can see, like if C is infinity, then in that case, uh, the final solution, so W star, ideally should be infinite, right? But that will not give you the trivial solution. So the only way for you to get the trivial solution was when you can ignore the second term over here, means C sum over epsilon I. And you can only ignore this term when my epsilon i's are zero, right? So when my epsilon i's are zero, it means no data point paid bribe to go to the correct side, right? So in that case, this is nothing but your linear separability case. It means you already have, I mean, you have a W star, which is linearly separating the data set, right? So this hard margin SVM that we had seen, correct? This will happen, right? Because if C is infinity, think about this. If C is infinity, ideally, this whole term should go to infinity in that case, right? I mean, since you want to minimize, but you want to minimize this. You want to minimize this, right? So the only way you can minimize this when my epsilon i's are getting zero is zero, and this will be zero only if the data points are not trained right at all, and that will only happen when all the data points are classified. I mean, the data points are can be separated linearly, and that was exactly the hard margin SVM that we had seen in week 10. Correct?
Yes, ma'am.
Okay. All right. So we wanted to now convert this primal problem to the dual problem to see like which are the data points which is important to our W star. Now we want to see in the case of soft margin SPM, when we were talking about the hard margin SPM, there we had seen like which are points are important. So the same we can do for here. So now the Lagrangian function, this would be what? This would be your objective, that is 1 upon 2 norm of W square plus C times sum over epsilon I, where I is varying from 1 to n, plus some. Now you have, since this is for every I and I is varying from 1 to n. So here I is varying from 1 to n. So you have n such alpha i's you will have. So you have sum over alpha i's, where I is varying from 1 to n, W transpose, or not W transpose, so you can write 1 minus. So 1 minus W transpose xi yi minus epsilon I. Correct? This is for the first constraint, this one. Now for the second constraint, again, you will have n such uh, epsilon I will have epsilon 1 greater than 0, epsilon 2 greater than 0, so on till epsilon n greater than 0. So you will have uh, another term here that will be sum over beta I of epsilon I. So you want to see when you are looking at the uh, uh, primal formulation, the primal function, the primal formulation, there you were converting your g of xi, which was your constraint, to be less than equal to zero form, right? So that is what we did here. So if we do 1 minus W transpose xi yi plus minus epsilon I, that will be less than equal to 0, right? So similarly here, what you'll have to do is minus of epsilon I will just write it here. So it will be minus of epsilon I would be greater, would be less than equal to 0, right? So this is now this will be your g of, or you can say h of xi. Okay. So now what is there? So plus sum over beta I times minus of epsilon I, where I is varying from 1 to 1. Okay. So this is your Lagrangian function in this case. All right. So if this is the Lagrangian function, now what will the dual problem become? So my dual problem, or not the dual problem, I mean this formulation can be written as, if you write it in the form of Lagrangian, this can be written as min uh, over W epsilon max of max over alpha greater than equal to 0, beta greater than equal to 0, this whole function. So I can just write this as L of W epsilon alpha comma beta, right? And from the strong duality condition, this can be equivalently written as max of, so max of alpha beta min over W epsilon, this Lagrangian function, which is, this will come here. Okay. So now this is my dual problem now. And now solving this dual problem will come to certain condition and see um, what is the important data points, basically. So what is my problem now? So my problem now is, so the dual problem now become max over alpha beta min over W epsilon, and this is half of norm of W square plus C of epsilon I, where I is varying from 1 to n, plus sum over epsilon I is varying from 1 to n, 1 minus W transpose xi yi minus epsilon plus sum over beta I minus of epsilon I is varying from 1 to n. Now this is my problem. So we need to solve this problem, right? So we need to solve this problem. Now, to solve this problem, what you have here is you want to maximize this part, right? And you want to maximize it for the variable alpha and beta, right? So now you have the variable alpha and beta, and you want to maximize this part. So to maximize it, what will you do? You will you will take the derivative and equate it to 0, and from there you can find out what your alpha is, find out what your beta is. So all that you can do, right? So um, before that, so like before solving this whole thing, this whole problem, we'll first do the inside part. So we want to maximize, so inside we want to maximize, minimize this objective. Now, this is my objective. We want to minimize this with respect to W and epsilon. So we'll basically fix my alpha beta. We'll fix my alpha beta. And then what will happen is once you fix your alpha beta, now this is the problem that you want to solve. Okay. So to solve this problem and to find your W star or epsilon star, you need to take the derivative of this. And this is nothing but your Lagrangian function, right? You want to take the derivative of this. So you will take the derivative first. Let's take the derivative with respect to W, fixing your epsilon and equate it to 0. So if you do that, what will happen? So if you differentiate this with respect to W, fixing your epsilon, so in that case, this part, I mean, dou L by dou W, this will become what? This will become just W here for from the first part, right? So W, second term does not have W, so it will be basically 0. Then the last part will also ignore because it doesn't have a W term. And then the derivative of the third part would be what? This would be plus sum over alpha I, xi yi with minus sign, right? So you have minus sign over here. So minus xi yi, right? So this is the dou L by dou W part, where I is varying from 1 to n. And now you equate this to 0. So once you equate this to 0, you get what? You get W star to be sum over alpha I xi yi, where I is varying from 1 to n. So if you look at this, this is the same solution that you had obtained when you were solving the hard margin SPM problem, right? So this is exactly W star that you had achieved. And we had also seen that this can be written as some, if you write it in the matrix form, this is some xy alpha. Okay. So W star, again, you get the same solution. But now what about epsilon? What about epsilon? So, so if you have to find this epsilon, what will you do? You will now fix your W and differentiate with respect to epsilon I, right? So you will have dou L by dou epsilon I. This is what you want to do and equate it to 0. So if you do this, you will get, so first term does not have epsilon I, so that will be 0. The second term, if you see, it has the epsilon term. So if you differentiate L with respect to epsilon I, that there you will get only C, right? You will have only C. Then for the second term, what do you get? Second term, this doesn't have an epsilon, so this goes away. Then what is remaining is alpha I epsilon I, right? So alpha I epsilon I, if you take the derivative with respect to epsilon I, you will get just alpha I, right? So that is with negative sign because you have negative over here. So you get minus of alpha I. Okay. Now for the third term, again, what is there? You only have beta I epsilon I. So if you differentiate this with respect to epsilon I, you get only beta I, right? So again, you have minus of beta I. So if you equate it to 0, what do you get? Equate it to 0, you get C to be epsilon I plus beta I. All right. So this is what we are getting as when we are solving for dou L by dou epsilon I. So this is what we get. Now, if you substitute these two values, so you substitute this W star into, okay, if you substitute a W star over here and you substitute this C also over here, then the solution that you get is going to turn out to be, so you had max of alpha greater than equal to 0, beta greater than equal to 0. Um, this term, again stays the same. So you have alpha transpose 1, which one, this is a vector, minus 1.2 alpha transpose y transpose x transpose x y alpha. But since you have this constraint now over here, that is C is equal to alpha I plus beta I, this will also get added over here. So now you have another constraint, which is alpha, one more, uh, yeah, one more constraint to check, which is alpha plus beta should be equal to C. So now this is the problem you have with you, all right? So, okay. So here, so now this can also be written as, so this you can also write it as max over alpha transpose W minus half of alpha transpose Y transpose X Y alpha. Okay. Now, see, alpha and beta both are greater than equal to zero. And what we are saying is my alpha plus beta should add up to C. So in the objective, like if you look over here, you don't have any beta term inside. So if you don't have any beta term inside, we can kind of ignore this, and that ignorance can be, that you can add it as, like since you are ignoring this beta greater than equal to zero, but it's still there. I mean, you know that this alpha plus beta should add up to C, and my alpha should be greater than equal to zero. So what we can say is that my alpha should lie between 0 and C. Okay. So now this is my problem that we want to solve. Okay. So from here, again, what you can see is that you have this X transpose X term coming over here. So this can be, again, this can be cardinalized, which will be useful. Any doubt till here? Okay. Okay. So now this is my problem. And now if we again take the two cases that we had taken earlier, which was for the primal problem, we were seeing what if C is equal to 0 and what if C is equal to infinity, then what do you get here? So again, we will test this. So when we test this, like if I take C to be 0, then C to be 0 means that what we are saying is that my alpha plus beta should add up to C, or my alpha should lie between 0 to C. But if C only is 0, it means my alpha star is going to be 0, right? So now if alpha star is going to be 0, and I know that this W star is equal to sum over alpha star uh, xi yi, right? I varying from 1 to n. And if alpha star only is 0, so from here, what do we get? We get W star to be 0. And this is exactly the same solution we had gotten for the primal case. When C was 0, we were getting that my W is equal to 0 is the solution, right? And from dual also, we are getting the same solution, that is W star is equal to 0. Now, what happens if C is equal to infinity? Okay. So if C is equal to infinity, again, this will be more like your hard margin case, hard margin condition. So because if C is infinity, my alpha can go to infinity. And if my alpha can go to infinity, this is again the same, uh, the hard margin SVM that we had seen. So this is again the hard margin SVM. And this is exactly what we had gotten for the primal case. All right. So this is what we have observed from this dual formulation. Now, what next we will see is the complementary slackness conditions. Complementary slackness condition. So when we were talking about just the SVM problem, so there, what we have seen is like at um, at W star, at the optimal point, we were getting alpha star times W transpose, time 1 minus W transpose xi by a. to be equal to 0, right? At the W star, this is what we were getting. Now, if we look at the primal, the soft margin SPM case, so this is for now soft margin SPM. Now, for the soft margin SPM, we will observe from this complementary slackness condition that what are the points which are important to us. Okay. So for the primal formulation, since in the primal formulation we are minimizing our objective with respect to W and epsilon. So let's say my W star, epsilon star are going to be the primal solution. And in the dual case, in the dual formulation, you have this alpha and beta coming in, right? Alpha and beta coming in. So suppose that my alpha star and beta star are the dual solution. This is what we will assume. So suppose my primal solution is my W star and epsilon star, and my dual solution is, let's say, alpha star and beta star. Okay. So this is my primal solution. This is my dual solution. Let's say that. Now, what does the complementary slackness condition say? The complementary slackness condition says that at optimality, you will achieve the first condition would be that my first constraint. So this term. So this term. So what will happen is, so at optimality, like for every data point, you will have this to be 0 and the second term to be also 0. Okay. So this can be written as what? This can be written as alpha I star 1 minus W transpose Xi. This is W star transpose Xi by I minus epsilon I star to be 0. And the second condition was that my minus of beta I star epsilon I star should be 0. These are for every I. All right. This is the complementary slackness condition says that at optimality you will achieve this. Now, um, now we will see like you have two conditions over here because you have two different constants. So you get two different conditions. Now, what can we conclude from here? So for that, we will split this into three different cases. So the first case, so the first case that we will talk about is what will happen if my alpha I star is equal to 0. The second condition that we'll talk about is what will happen if my alpha I star lies between 0 to C. And the third condition would be what would happen if my alpha I star is equal to C. And these we are able to say from here, right? Because this is my constraint for this problem. The constraint is that my alpha should lie between this restriction is that my alpha should lie between 0 to C. So what will happen if you take alpha to be exactly 0? What will happen if you take your alpha star to be exactly C? And the third is what will happen if your alpha lies between 0 to C, right? And remember that my W star, the optimal W that we had obtained for even this problem is that my W star should be the linear combination of my data point, that is sum over alpha I, xi, yi. Okay, so we'll keep these in mind. Now, if we take my alpha I star to be equal to 0, then what can happen? I know that my alpha I plus beta I is equal to, it should be C, right? We know that. So if this is equal to C, and if I'm assuming that my alpha I star is equal to 0, then in that case, what we can say, so since we're talking about the optimal point, so my beta star should be equal to C. This is what we can say. All right. So if my beta I star is equal to C, then from the complementary slackness condition, you have two different conditions now, right? So the second complementary slackness condition says that my beta I star epsilon I star should be equal to 0. But if we obtain that my beta I star is equal to C, it means my epsilon I star should be equal to 0. So from here, we can say that my epsilon I star is equal to 0. Okay. Now, from the first complementary slackness condition, if I get epsilon I star to be equal to 0, and my constraint was this one, right? The W transpose Xi yi plus epsilon I is greater than equal to 1, right? So our constraint was that W star transpose Xi yi plus epsilon I should be greater
Ma'am,
than equal to 1. Yeah,
can you explain from epsilon I equals to 0 how we concluded this? I
how we
didn't get.
consider epsilon I to be 0. Okay. See, this is clear that my beta I star should be equal to 0. This is
Yes,
clear,
ma'am.
right? Okay. So if my beta I star is equal to C, then I will go back to my complementary second condition. This is my first condition, this is my second condition. So my second condition says that my beta I star epsilon I star should be equal to 0, right? So if my beta I star is equal to C, then for this condition to hold, my epsilon I star has to be equal to 0,
Yes, ma'am.
right? So that is why we are able to say that my epsilon I star is equal to 0.
Got it, ma'am.
Okay. Now, what was my constraint for our original problem? Our constraint was that my W star transpose Xi by I plus epsilon I should be greater than equal to 1. Okay. But now, if my epsilon I star is equal to 0, it means that what I can say is that W star transpose Xi yi should be greater than equal to 1. Correct? This is what we can
Yes,
do. Now, if we are able, so what we got is that if my alpha I star is equal to 0, it means that T W star transpose Xi yi should be greater than equal to 1. All right. So if I'm saying that, and what do I know? I know that my W star is equal to some linear combination of Xi yi, right? But if my alpha I star is equal to 0, then in that case, these are the points that are least important to us. They are not useful for my W star. We know that, right? So now the question is like if my alpha I star is equal to 0, uh, then these points for the points for which alpha I star is equal to 0, these points are not useful at all for my W star because they're not playing any role, they're not contributing anything towards my W star. From here, we can say that. But now the question is, where do these points lie? So these point as we can see that these point will lie on these outside this hyperplane. So okay, so let's say this is my W star. So this is my W star, and so this is my hyperplane where this is set of all x where W star transpose xi is equal to 1. And this is set of all x for which my W star transpose x is equal to -1, right? So now what are we getting is if your alpha star is equal to 0, then all the points should lie either on this plane or outside this plane. So either these points will be here or it will be here. So all these points which are lying in these regions are not important to my W star. So this is what we are achieving from this case. Now we will move forward to our second case where we are saying that my alpha I star belongs to 0, comma C. So if my alpha I star belongs to 0, comma C, and what we know is, so this is basically saying that my alpha I star strictly lies between 0 and C. And what we know is my alpha I star plus beta I star is equal to C, right? From this condition, we cannot say anything where, like, like what exactly my alpha I star is. But what we know is it should strictly lie between 0 to C. So if my alpha I star strictly lie between 0 to C, then and my alpha I star plus beta I star is equal to C, then from these two conditions, what we can say is that my beta I star should also lie strictly between 0 to C. Okay, this is what we can say. Now, if my beta I star strictly lies between 0 to C, then from the complementary slackness condition 2, so if my beta I star is some positive value, which cannot be 0, and for the second condition to be satisfied, my epsilon I star has to be equal to 0, right? So from here again, what do we get is that my epsilon I star is equal to 0. Okay, this is what we get. So if my epsilon I star is equal to 0, then from the first condition here, which is alpha I star 1 minus this term, what we can say is, what we can say, this is from the first condition, that my 1, this is what, 1 minus, yeah. So 1 minus W star transpose xi yi minus epsilon I star should be equal to 0. Okay, this is what we can say. Now, if this is if this is equal to 0, then and if epsilon I is also equal to 0, then from here what we can conclude is my W star transpose xi yi is equal to 1. Okay, so if my alpha lies between 0 to alpha I star lies between 0 to C, strictly lies between 0 to C, then what we are getting is that my the points which are contributing, I mean, if alpha i's are strictly positive, then I know that the points for which alpha i's are positive, they are contributing towards my W star. And where are these points lying? These points will lie exactly on the hyperplane. So if this is my W star and um, this is my set of all xi's for which W star transpose xi is equal to 1. This set of all points for which W star transpose xi is equal to minus 1. So these points will lie on these hyperplane. So if this is my uh, all the positive points, and maybe these are all the negative points. So this is what we can conclude from the second case. Okay. Now, all right. So this was about when alpha I star is equal to 0 and alpha I star strictly lies between 0 to C. So now what next? So what we can say now is like what will happen if my alpha I star is exactly equal to C. So remember that my W star is the linear combination of the data points. And if alpha I star is strictly C, it means that the points that the points that we will get from this condition are the points going to be the most important to our W star, right? So If alpha I star is equal to C, then from the complementary slackness condition, we can say that my beta star should be equal to, not complementary slackness condition, this condition that alpha I star plus beta I star is equal to C, we can say that that my beta star is equal to 0. Now from complementary slackness condition, what if my beta star is equal to 0, then what I can say is that my alpha I star has to be greater than equal to 0, right? So from here, we can say that my alpha I star has to be greater than equal to 0. Okay. So if my alpha I star has to be greater than equal to 0, then from the first condition where alpha I star, this term was going to be equal to 0, what we can say is, since alpha I star is equal to C, so this will go towards the right hand side and it will be 0. So what we are left with is 1 minus W star transpose xi yi minus epsilon I star has to be equal to 0. Okay, this is what we get. So from what we can say here, we can say that my epsilon I star is nothing but 1 minus W star transpose xi yi. And what we have here is that my epsilon I star has to be greater than equal to 0. So if epsilon I star has to be greater than equal to 0, now we will have that my 1 minus W star transpose xi yi has to be greater than equal to 0, right? And what can we say from here? What we can say is that my W star transpose xi yi has to be less than equal to 1. So what we got is that if my alpha I star is equal to C, then in that condition, uh, my W star transpose xi yi has to be less than equal to 1. All right. So this is what we get. Okay. So now the question is, where do these points will lie? So these points will be, so if this is my W star, and this is my, again, set of all xi for which W star transpose xi is equal to 1. These are set of all xi's, or this is not required actually. This is set of all xi for which my W star transpose xi is equal to 1. So what we are saying is, since this is my, this is in boundary, so any point that is on this side will be contributed towards, they will be positive level and or +1, other side will be -1. So from this condition, uh, what we are saying is that anything that lies beyond this line, so all this, any point that lies here will be will be very important to for our data point. So this is what we can conclude. So if you're saying that any point that lies beyond this line, it means that, uh, I mean, even if some points are over here, or some points are actually on the right side. I mean, if it's positive level, it's actually on the positive level, but it is not correctly classified with. It is not classified with the correct margin. It is classified with less margin. So these points, or it might happen that there are some points which was actually a positive level, but they were kind of like um, treating as negative level, right? So these points are also important for our W star. So from these three cases, from alpha s is equal to 0 and all these three cases, what we can conclude is the most important point for our W star are those points which are either incorrectly classified, so the points which are over here, or the points which are classified correctly, but they're not classified correctly with the enough margin. Okay, so this is what we get. Or from the second case, these points are also important because for these points, my alpha I star was lying between 0 to C. So the points which are on the margin, or the points which are incorrectly classified, or the points which are correctly classified with less margin, are the points which are important for RW star. Yes, Ravi.
Ma'am, can you explain the last graph once again? What you told?
Hmm. So from here, from this condition, that is W star transpose Xi yi less than equal to 1, this is the graph that we get, right? This is the reason that we have, correct? This is fine.
Yes.
Now, uh, so saying that this is the reason, it means the points which are here, I mean, the points which are on this side are important to us. But remember that you will also have this, right? And this will be a set of all xi where your W star transpose xi is equal to -1. Okay. So I know that from the previous two cases, I mean, from the first case, I know that any point that lies beyond these two hyperplane are not important to us. So anything which will lie here, um, which will lie on this side, which will lie on this side or on this side, that is outside this hyperplane. I know from the first case that they're not important to us, correct? So I don't have to worry about it. From the second case, what we got is that the points which are exactly on these hyperplane, they are important to us. Okay. And from the third case, where my alpha I star is exactly equal to C, what we are saying is that the points which are in this region, um, the points which are in this region, they are important to us, right? Anything that is after this, beyond this. Now, I know that in this region, you can have points of two kind. There can be points of, there can be point like this, which was, and this is my decision boundary, right? So there will be point like this blue color point, which are classified correctly. I know that since this is my decision boundary, any point that is on the right side of the boundary is going to classify as +1. Anything on the left side will classify as -1. So there will be points which are correctly classified, but they are not classified with enough margin because we were looking for at least this margin, right? So these are some points which are important, which are classified correctly, but not with enough margin. Then there can be point of these kind, which is toward the left side of the decision boundary, right? Uh, and to the right side of the negative, I mean this hyperplane. So these are the points that these points can also be the points which were kind of outlier, you can say. I mean, these points were I mean, these points were labeled as in my training data set as positive, but it is on the left side of the decision boundary. So these are the points that are the most important to us for our W star. This is what we are saying. Is it clear?
Yes,
Ma'am,
ma'am.
Mhm.
the points lying on the hyperplane for second condition,
Mhm.
uh, why these are important to us?
Because my alpha I star belongs to 0 comma C. And you can see that they are not, I mean, 0 is not closed here. So there can be no alpha i's which are equal to 0, right? So if my alpha i's are strictly positive, then from this W star, which is nothing but a linear combination of your xi, yi, I varying from 1 to n. So if alpha i's are strictly positive, it means my data points, these data points are important to us, right? Because they will contribute towards my W star.
Okay, okay.
Yeah, that is why they're important. But on the other hand, when my alpha I star is equal to 0, what we got is that it should be here. I mean, it should be outside these hyperplane. So any point that is on the hyperplane or outside the hyperplane, they can be not important to us. Okay, so this is what we are seeing from here. So yeah. Okay, so one more thing. So like I had said, this is we're taking from primal, but this is also from coming from your complementary slackness condition 1, because my alpha I star was equal to 0. So if alpha I star is equal to 0, my this term has to be positive. So if this term has to be positive, it means my 1 minus this term should be greater than equal to 0, right? So if this is greater than equal to 0, it means my W star plus this term should be greater than equal to 1. And that is how we got this. Earlier, I had said that we are taking this from the primal thing, but this is actually a complementary slackness condition 1. But
Ma'am,
again,
this
they are same thing. Yeah. Tell me.
it can also be zero.
What can also be 0?
And this second term, what you explained right now.
Just I mean this one.
Alpha into the whole.
This term, right? So what I said is you have alpha I star is equal to 0. From there, we got that my epsilon I star is equal to 0. So if I look at my complementary slackness condition 1, so from here, I mean, since my alpha I star is equal to 0, then my second term, which is 1 minus W star transpose xi yi minus epsilon I star has to be equal to 0, has to be greater than equal to
Um,
0, right? So from here, what we can say is that my W star transpose xi yi plus epsilon I star has to be less than equal to 1, right? And this is what we have written here. It is greater than equal to 1, is it? Uh, Greater than equal to 0. This is what we get, right? Hmm. No, this is not correct then. This is from the primal thing, what we have seen before. Okay, so just remember that um, this is this condition is this one, this case. W star, W transpose xi y plus epsilon I has to be greater than equal to 1. And this is what we are using over here. Okay. So what we got here is like when your alpha I star was equal to 0, the points which are outside this hyperplane are not important to us. The point when my alpha I star belong to this open interval 0 comma c, then these points I know are important to us, and these points lie exactly on our hyperplane. And the third case was when my alpha I star was exactly C, and I know that these are the points which will be the most important to us. And these points are the points which are either incorrectly classified or they're classified correctly, but with not enough margin. So In summary, this is what we have seen for soft margin STM. Any doubt here? Okay. All right. Next, next we'll move to some another topic, and from here we will talk about bagging, the overfitting and the underfitting of the model. Look at overfitting and underfitting. Okay. All right. So what do we want? I mean, when we say the overfitting and when we say underfitting, what do we mean here? So when we are seeing overfitting, it means we are also fitting the noise, right? We are, in a sense, we are trying to come up with a model which has a training error almost zero. This is what we mean by overfitting. So while doing this process, when you are trying to overfit, when we are fitting this model, in that process, you are also fitting the noise along with the structure. So thinking that what you're doing is a structure, but when in actual it was a noise that you're fitting. So that is when we call a model as overfit model. And when you're talking about underfitting, it means that you are missing out the structure. When you're thinking about that, the structure was a noise. So, for example, so the example that is given in the lecture. So, one example that is given is suppose that my data point had this structure. I mean, the true structure was this. This is just an example. So suppose that the structure was something like a sinusoidal wave. So you had something like this. Okay, this was my structure. This is my x. This is my y. Now, let's say the data point that are given to you uh, is not exactly on this curve, but maybe what you have observed is something like some noisy version of it. And let's say what you have observed is something like this. Something like this. So let's say what we observed. Maybe one we can put here. Okay. So suppose this is a data point that you have observed. It is not exactly on your Y, but kind of there is some noise here. Now, if I just plot these lines, so what do we get? So what we will get is if I plot, if I just see these points, I'm not going to draw the curve. I'm just going to plot the same point here. This, this, this. Okay. So this is the data point that we saw. Now, if we look at this data point, and if I have to fit a model, uh, a very like the obvious, like very simple model that one can fit here is the linear model, right? And maybe it will some the model that you fit, or maybe just this looks quite linear. Let's put this over here. Okay. This point will be here. So maybe someone can fit a line like this. Maybe this is the line. Okay. So this is a very simple model that one can fit, right? Looking at this data set. But in reality, these data sets were coming from a sinusoidal wave, right? So here, what we saw, what we thought is that all this is noise in the data set. We are thinking of this as noise in the data set, and thinking that this is a noise, we are missing out on the structure of this data set. So such kind of model, we call it as underfit. So these are underfit model. These are underfit model. Then another thing that can happen is when you can overfit it. Like now, let's say you observe the same data set. So for the same, so you have X here, you have Y here, and you have these data set. So you have okay. So this is a data set. Now for the same data set, let's say I underfit the model and saying that I am underfitting the model. Maybe I can fit a polynomial, a higher degree polynomial, and maybe it can go like this. Suppose this is the polynomial that I fit. Now, in order to fit this polynomial, since we have kind of achieved the structure that the true structure was sinusoidal, and in some way we are somewhere closer to that structure. But what we are doing here is, in order to achieve this training error to be zero, we have kind of also fit the noise along with it, right? So such kind of model is what we call it as overfit model. So these are my overfit model, and this is my underfit model. So underfit model is when you are also fitting, you are missing out on structure, thinking it is a noise, and overfit model is you are missing out on, you are overfitting in order to fit the structure, you are also fitting out the lot of noise. So these are this is the difference between these models. Now, what will happen is like when you have, let's say, an overfit model, and this is like just given some, I mean, for some data set that you observed, you have formed this, I mean, this is a polynomial that you fit. Now, what we can also say is if I give you, I mean, you have the same data point with you. And this orange data point that you see, you have the same data point that you have with you. But now, if I give you, now if you have to fit another polynomial, so you will observe some different set of data point, and you will fit a model. And let's say you fit some another model over here, and that another model which is also underfitting. So let's say this is my another model, the screen curve. Okay. Now again, this is an overfit model because the training error is zero. So what will happen is like if I take any test data set, so let's say this is my test data set. This is my test data set, and this should be my true Y, right? So this is my true Y. This is my Y. Now, if I look over here, and if I take this as my, or maybe let me just extend this. Let's say this. Okay. So let's say this is my, instead of this point, let's say this is my test data set. Now, for this test data set, this is my Y, right? I mean, this is my true Y. Now, if I look over here and if I see the test data point, so this is my, let's say, X test. I'm taking the same X test. Okay. So if this is the X test, what we are getting is where my ideal Y should have been over here, somewhere here. Now it is, we are getting this as Y hat, right? So this is the error that we are getting. Okay. Now if we are fitting some different model, which is in green color here. So if we fit this model, then for this case, the error that we will get, so the true Y is here, right? For the green curve. This is my W hat, Y hat. Now for this Y hat, where my true Y was this, now the error that you're getting for this model, which is in green color, which is also an overfit model, the error that you're getting is something of this length. This is my error, right? Now, what can happen is like you can also take some another data set. I mean, you're observing some another data set and you fit some different model, and that model is also underfit. So for every overfit model, sorry. So for every overfit model that you take, you are going to get you are going to get a very high the variance that you're going to get in the error is going to be very high. So for this blue curve where my error is this much, for the green curve I got the error is this. Then for the some other curve that is fit, maybe my y hat can come here also, it can come here also, it can come anywhere because we are under overfitting the model. So what we are saying is that in the overfit model, you have a very high variance. So overfit model will have high variance but low bias. Why low bias is because you are somewhere maintaining the structure. So since you're maintaining the structure, the bias is low, but the variance that you're getting is quite high. While when you look at the underfit model, so in the underfit model, now if I take this X test, so this is my X test, right? So this is my X test. So if I take this X test, so and where my true Y should have been here, right? But the Y that I'm getting, Y hat that I'm getting is over here. So how much error that I am getting? The error that I'm getting here is this much. Now let's say again if I observe some another data set, I will have some different line, right? And someone can fit a more simpler like again it is going since we are saying simple model, so some linear regression model one can fit, and maybe someone can fit a line like this or a line like this, something like that. One can fit, right? So here, since one would fit this model, this linear model, then the error that one can get where my true y was supposed to be here. So if I talk about this line, my error that we are going to get is almost zero, I mean no error. For this line, you are going to get this much error, right? For some other line that one might fit, maybe I'll get some this much error. So the error that you are getting for these underfit models, they are not too high. So they will maybe they will lie somewhere around here to there. It cannot it cannot vary too much because you're only fitting this underfit model, and these are the linear model. These are the only possibilities. Maybe a range you can get, range of values of y you can get in this. So kind of the variance is low in the underfit model, but the bias is quite high because we are not maintaining the structure. So underfit model are the high bias model, but less variance. Okay. So this is a major difference between an underfit and an overfit model. So every time, like
Visualize
when,
bias.
sorry, Hmm?
How we can visualize
Hmm?
bias, ma'am?
How can you visualize bias? Bias is see this is the curve that you see here. This one.
Mhm.
This is my true structure of the data set. I mean, this is sinusoidal wave. But what you are doing is you are making a very simple model. I mean, given the data set, you just what we have done is we have just done a linear model, right? And because of this, I mean, we are since we are thinking that these are noise, but they are not noise. I mean, you're fitting the noise, but uh, sorry, you're not fitting the structure thinking that these are noise, because this is not the structure that my actual data set has, right? So from there, we can say it is this model is biased.
Okay, due to structure is not similar, right?
Yeah,
Okay.
that we can say. Yeah.
Uh-huh. High variance means less error also.
No,
Like,
high variance means more error, right? What? So here you can have your y hat to be anywhere in the line because you are overfitting the model. So you can get any polynomial which are passing through these orange data points, making. I mean, you can have some curve which are like this and this. It goes on like this, right? Or like uh, it will completely satisfy these points, making the training error to be zero. But the error that you are going to get between like any test data point that you get, the for that test data point, the error that you will get for your y hat, for your label is going to be quite, the variance in that is going to be quite high. So that is why it's called high variance model.
hmm,
Okay. So these are the
okay,
major differences.
okay.
So
Variance is okay, fine.
hmm, so what we are saying is like, so whenever we are trying to like whenever you have some hyperparameters, and for those hyperparameter you are using your cross validation, different cross validation techniques to get those hyperparameter. What you're trying to do is you are trying to kind of balance this bias and variance
Hmm.
while finding those cross validation. So there is always a trade-off between this variance and bias. So you might remember from your stats like there's bias
Hmm.
variance trade-off.
Yes, yes.
So this is what we mean. So all right. So to deal with this bias variance trade-off, what we're going to introduce is some ensembling classifiers. So ensembling classifiers, there are also some learning algorithm. Um, so ensembling classifiers. And these ensembling classifiers, which we can also call as meta classifiers. Okay, so they're also kind of learning algorithms. Now, for this to like deal with this bias variance trade-off, we are going to see two different ways. So one is what we call as bagging, and other is what we call as boosting. Okay. So what bagging means is this is nothing but bootstrap aggregation. And what boosting, so in boosting, we'll look at another algorithm we'll talk about later. So first, let's talk about bagging. So before we start this bagging technique, what we are going to see one small statistical technique like how this can be useful for these uh, these methods. Okay, so suppose that you have some true value of I mean you have observed some data point from this let's say mean is equal to 5. So you have observed some data point from this distribution. Let's say you have some value x1, x2. These are some realization that you have. Let's say it goes on till xn. Okay. Like in reality, we won't know from which distribution you have observed the sample, but like for now, let's think that this is the distribution from which my data points have come and forget about it. So what only we have observed are these data points. Okay. Now these are the data points, and now we wanted to understand like what was the estimator of my mu. So like these are data set that we observed, and what we said, let's say they're coming, all I'm saying is that they're coming from a normal distribution with some mean mu and variance, let's say 1. Okay. And even though we know, I mean, here we are writing that from this mu is equal to 5, this data set is coming from. I mean, so it is ideally coming from normal with mean 5 and variance 1. But in reality, we don't know that. We only observe the samples. Okay. So now if we have only observed this xi, x1, x2 up to xn sample, and they're coming from a normal distribution with some mean mu and variance 1, my goal would be to estimate this mu, right? So to estimate the mu, I know that a very popular technique to estimate for estimation is the ML estimation problem, right? Your MLE technique. So if you do that, I know for a normal distribution, this mu hat should be just sample mean, right? This mu hat should be sample mean. So this is the best, like in a way, the best estimator that we can have for mu. But this is not the only choice for your, this cannot be the only choice for your estimator, right? I know that my estimator is just a function of your random variable. And now here my random variable are x1, x2, x3 up to xn. So what we can also say is like one estimator that we can define is, let's say, mu1 hat is my first data point. My mu2 hat is, let's say, x2, second data point. Mu3 hat is x3, my third data point. So on till I can define some estimators like this, which is obviously correct. There is no doubt, right? These can also be, these are also a valid estimator. And this is also a valid estimator, right? So to check, like, since all are these are valid estimators, so we have x1, x2, x3, so on till x bar. These are all the estimator that we have. And I know that all these estimators are also unbiased estimator, right? Because if I take the expectation of mu hat, there also we will get mu. And if I take the expectation of any mu hat I, which is any of these, I know they will also going to be mu. So there is no difference. I mean, why should one choose my x bar and why not these xi's, right? So this is one question that you may ask. Like, since all these estimators are my unbiased estimator, then why go for x bar, right? So what will happen is, like, if you define your estimators as x1, x2, x3, and so on, right? So, I mean, these are just like, if I'm saying my estimator is x1, it means in the sample that you have observed, any first variable, you will take it as you will take it as estimator. So that is with respect to the sample you observe. Now, let's say if I observe some different sample, I'm going to get a different x1, right? So maybe as at some time I can have my x1 as, let's say, 1. Some other time I can have my x1 as 7 or 8.5 or 100. Anything can happen in my x1. So the variability that you will see here is going to be quite large, right? So that is what we don't want. So that is why this choice of estimator, where we had chosen my mu hat to be x bar, this is the most ideal estimator that we can have, because this is not just my unbiased, but in a way, like when you are averaging all this, so what is my x bar? My average is x bar is 1 by n, x1 plus x2 plus up to xn, right? So you're averaging your data set, right? So this, when you're averaging your data set, it is not only that it is making the estimator unbiased, but it is also reducing your variance, right? So this will make sure that your variance is less. That was not happening when you're taking each of the individual entries as the estimator. Like, they were unbiased, but the variance were quite high. So that is why they were not really good. So this is the technique that we are going to use in our bagging.
Now here it can also happen like every time maybe we got same variable. There is no variability when the bias is not zero. Like you say na, a bias and variable trade-off. Here it is not happening. Whenever it is unbiased, right, then it is also less. Then how that will happen? Like
We
that trade-off is not
uh,
there.
here,
Uh-huh.
this one,
Yes, yes.
because you know that what is the variance of this. I mean, you are take now in this case, what you are doing is you are adding all the terms, right? And you're also dividing it by n.
Yes. Yeah, yeah.
So this will, in a sense, it will reduce the variability. Like this is like one sample you observe, you get some sample mean. Another
Mhm.
sample you observe, you will get some another sample mean. So if you collect all these sample mean, like uh, all these sample mean, if you collect,
Mhm.
maybe depends on how many times you have collected the data. You every time you get different sample. So the
Yes.
variability that you will see in this will be less.
Okay, variability among samples. Different
Uh,
means of samples of mean. Sorry, mean of
yeah.
samples. Yeah.
Correct.
Okay.
Yeah.
Okay.
Okay. Because you're taking sample mean. So that
Uh-huh.
is why the variability will be less. So this is the idea that we are going to use in our bagging technique. So in bagging technique, what this bagging technique is saying is you have to do bootstrap aggregation. So all these ensembling classifiers, it is trying to do is these are trying to convert the weak learners. So I will tell what also is defined as weak learners as. So it is trying to convert the weak learners to the strong learners. So like what is weak learner is that anything that works a little slightly better than random. Okay, like if you take your some test data set, and if it maybe it is just slightly higher than what it will work without fitting any model, like in random, let's say tossing a coin. Um, like if you fit a model and you get maybe slightly more than 0.5, we can say it is a little better in a sense. Okay, so just something like that. So in these ensembling classifier where we are going to see bagging and boosting, what they are going to do is they are trying to convert weak learners to strong learners. So in weak learners, so what are my weak learners? So all my underfit model and the overfit model. Okay. So these are my weak learners. Because let's say if I'm overfitting the model, so in a way we are trying to fit a lot of noise also, making the training error zero. So this is working slightly better than any random model, any random performance, but it is not a good model, right? So we'll start with some weak learner. I mean, so we'll start with some overfit model and we'll try to make it the ideal or the strong learner. Okay. So so first let's start with bagging. So in bagging, so my first technique is bagging. So bagging generally, so in short, what you can think of it as, it reduces the variance. And um, since it reduces the variance, and we saw that if we take the average, it helps us in reducing the variance. So we'll see how it works. So suppose that if you have the data set, which is D1, D2, so on till DN, sorry, DM. Okay. These are your data set. And these data set are independent. So what we're saying is DIs are independent. They are independent. And here, what we are also saying that each of these DIs, they will have n points. So you will have x1 y1. So since I'm writing for data point I, data set I, so this one. So x2, y2, this is for I data point, and xn, yn. Okay. So suppose this is my, you have m, this is m here, okay? This is not m, this is m. You have m independent data set with you. You don't have just one data set. What we are saying is you have m independent data set with you. Now, how does each of the data set look like? Each of the data set looks like this. You have each data set has n different points. You have n xi's, n yi's. And here again, each of the xi's, so each of say xj I will belong to RD, and your yi's or yj's will belong to your label. Since we're talking about the classification here, so it will belong to plus or minus one. All right. This is how your data set is. So what can be done is, since you have m different data set now, so for each of the data set, so you have with you have D1, you have D2, you have till DM. You have m independent data set. Now the thing is, let's say these data set, let's take one example of a classification model. Let's say decision tree we are talking about. Okay. So for let's say for the data set D1, we fit this decision tree. So we get some decision tree, and what we are saying is all these decision trees will fit the decision tree for all these data set. Okay, and we'll fit it in such a way that they all are overfit. Okay, making it a weak learner. So on all these m independent data set, we are overfitting my decision tree, making it a weak learner. Now each of these decision tree will have a classifier. So let's say the classifier that I get for the first one is, let's say, H1. For the second, let's say I get H2, and so on till, let's say, I get some classifier HM. Okay, and these are my decision tree that I get now, and all these decision trees are overfit. Now we will use the idea of averaging. So what we will do is that my H star, now aggregated classifier H star X, would look like, you take the sign of the average of each of these classifier, HIX, where I is varying from 1 to n, right? So this is what we can do. But what will happen is that you will not have with you some m different data set. You will only have one data set. So what we have done here, like we were talking about that my averaging will reduce the variance, right? And for that purpose, we tried, and what we said is, let's say we have m different data set, and for each of the different data set, we fit those H1, H2 up to HM. We got these classifiers which were overfit decision trees, and we have aggregated all these classifiers, and we said we took the average and it should reduce my variance. Okay, this is what we are saying. But in reality, you will not be given some m different data set. You will not. This is not possible. In reality, you will have in real world you will have only one data set with you. So if you have just one data set with you, how can you use this idea of averaging to reduce the variance for this overfit model? Okay, so one very simple way to do it is, like, since I know that my data set, since I have one data set with me, and my data set is going to look like x1, y1, x2, y2, so on till xn yn. Okay. Now if this is my data set and I know I have n independent points, n data points. So if I want to use this averaging method, what we can do is we can split this data set into m equal parts, right? We can equally split this data set in m part. So let's say this is first part, second part, third part, so all till m parts. So if you equally split this data set D in m parts, then what will happen is that if m is quite large, then each data set will have like very small, very less, very less points in each of these data set, right? So let's say if I equally split it and I come up with D1, D2 up to DM, then in that case, each of the data set, though they are going to get equal number of points, but they are so small that they're not going to capture, like they're not going to be very useful in the training, because many of the features you will lose out because they are so spread out in different data sets. So this is also not an ideal case to split into m different parts. So what we can do is to overcome this situation, we will use the bootstrapping. And what bootstrapping means is, what is bootstrapping? Bootstrapping is nothing but sampling with replacement. Sampling with replacement. Okay. So now again you have this data set. I mean, you have the data set. It's the same data set that you have this what we have written over here. Now, what do you do in Bootstrap? So in Bootstrap, what you do is like, since the idea is that you want m different data sets, right? So we'll create m different bags. So let's say this is uh, this is one bag. This is this is one bag. This is second bag, and so on till we'll create some m bags. Okay. So and I have n different data points, right? So again, in each of these bags, I will try to get n different, n not n different, we'll get n data set in each of these bags. And how we can do it is like, let's say I want n pair of values in my first bag. So what will I do is I will, from this data set, x1 to xn, I will pick out one data set. Let's say I get some, let's write it as small x1, x2, and call it as capital X, maybe capital X1 as my first, like the first value that I get is, let's say, x1. Then I put this value again in this data set, and then I again pick out one value. Again, let's say I get some x10. Again, I keep this x10 in the bag, and again I pick up some value. Let's say I get some x1 again, right? Then again I put it back. Let's say I get some x100. I put it back, I get, so let's say x98 or something, right? So in this way, you can have n data set in this path, but in this n data set, it is not going to happen that all these n data set are same, right? It is all going to be like there will be some data points which are repeated. Correct? This is the idea behind sampling with replacement. So in the same way, you can have m different bags, and each of these bags will have n different, not n different, n data points. Okay. So this is where the bootstrapping is working. So now you have D1, you have D2, and let's say you have DM. Each have n points. So now again, for this, now you will do what we have done over here. For this D1, D2 up to DM, you will fit, you will have a weak learner. You will, and weak learner as in like you will overfit a model. And for this overfit model, you will get some m different classifiers, H1, H2 up to HM. And then you take this H, and then you do this H star, which is sine of 1 upon n sum over HIX. So this will be your, and this step that we are doing over here, this is called the aggregation. So bagging, which was bootstrap aggregation, this is what we mean. So my first step was bootstrapping. So this is where we were doing bootstrapping. And the second step was we were doing aggregation. So what we said is like now uh, using this bagging technique, we are able to come up with a classifier. We are able to come up with a classifier which has comparatively lower variance, right? Because we are averaging it out. So we'll say that this will have a lower variance. And I know that since this was an overfit model, this will also have some low bias in it. So this is a now what we so from a weak learner, we are able to make this as a strong learner. This is the idea. Okay. Um, so, one more thing over here that see, each bag I know is going to get n data points, but there is a possibility that there will be some data point which is not available in a bag, or there will be some data point which will be repeated in a data, which will be repeated in a bag, right? So, what is the probability? Like, if I have to look at the probability, like let's say, what is the probability that my X30 was not in a data set? Okay, so probability that my X30 is not in D1, that will be just 1 minus 1 upon 1 upon n, when assuming that you have n data set, this will be the probability, right? So this is the probability that a data set, any data set, is not in the bag, right? But it is not that, because see, you have in any bag you need n different endpoints, right? In any bag you need endpoints. So probability that in my first, like when I picked up the first data point, probability that let's say my xi was is not in this data, is not in this dj, let's say, is 1 minus 1 upon n. But if I'm finding the probability that this data set has not even come in this bag, then it means that every time that I'm picking a data point, this has never come. So that probability will be 1 minus 1 upon n to the power n, right? So this is the probability of any data point being not in the bag. Okay, this is the probability that we get. So if this is the probability that we have for any data set to be not in the bag, then what is the probability for any data point to be in the bag? That will be just 1 minus 1 upon n. Okay. So if n is large enough, as n tends to infinity, I know that this term that you see will tend to zero. Sorry, tend to e, right? This we know, right? Not e. Sorry, this is 1 upon e. This tends to 1 upon e. Assume that we know this for large enough n, this tends to 1 upon e. You must have seen this when you're doing some sequences and series. So this is quite popular. So if n tends to infinity, then this goes to 1 upon e. So what we can say is that probability of any data point to be in a bag is going to be 1 minus 1 by e, and which is roughly 67%. So this is the probability of any data point to be in a bag, right? So it means there will be some 32 to 33% of the data set which will be repeated in the bag, right? This is what we can conclude from here, right? So right. So if this is the probability for any data set to be in the bag, it means that uh, in another way we can say that some 33% repetitions are happening on average in each bags. Correct? This is what we can conclude. Now, since the way we have picked out the data point for in each of the bag, then using this bootstrapping technique, the data set that you're going to get in each of the bag in D1, D2 up to DM, they're all going to be in a way different to each other. They're not same, right? So if for every different data set you're learning a weak, you're overfitting a weak learner, then in that case, what will happen is that um, like what you're learning is all these H1, H2, and HM, right? These are the classifier that you get. And these are classifiers you're getting for different data set. So getting a different set of data set for every different bags, this is making sure that the data set that you have in each bag are um, in a way uncorrelated to each other. Okay. So, and this will help you in like minimizing the variance more. It will help in variance reduction. So, like for this, to achieve this, what we're going to use is the technique called random forest. So, random forest is also the feature like random forest is also like a feature bagging technique. Um, and what it helps in is like um, these H1, H2, and HM, all these weak learners that we get, the weak decision trees that we get, we want to make them as uncorrelated as possible so that they uh, they kind of like when we aggregate all these HIs and find our this, then this H star should have a much lower variance. This is the idea for random forest. Um, any doubt so far before I proceed? Okay, all right. So now we'll move to random forest. So random forest, remember that we want to do the random forest because we want to we want our learners to be as uncorrelated as possible. This is the idea. And the more less correlation is there, the lesser variance you can the more the variance you can minimize. This is the idea. So what we can do, so we'll stick to our decision tree example. So in random forest, the first is still same, which is you're bagging your decision tree. So you're bagging the decision tree, and when we're saying bagging the decision tree, basically you are overfitting the trees. So mm, like after this bagging, what you want to do is you want to feature bag. So next step is feature bagging. Okay. So okay. So when you have the decision tree, like how do you design it? So you will have set of features and feature value pair basically, and you will pick up those feature from set of all those D features. You will pick up those feature value pair that will have the maximum information gain, right? This is the idea behind the decision tree. Like this is how you pick up the feature value pair for each node by checking the information gain for every set of features that we have, right? So now since we have some D different bags now, so you will have some D different M different decision trees. So now with for M different decision tree, what you will do is uh, all the trees that you will have. So you have D1, D2, so on till DM, right? This is the bagging that we have seen. So now you have these bags, and you will overfit those trees. So while doing the overfitting, like what you can also do is like while making this decision tree, what you can do is you can feature bag the features. So what do you mean by this is like where while designing the trees, you were like looking at all the features, and from there you were deciding which feature to choose for our node. So let's say if you have F1, F2, up to FT features. Okay. So in feature bagging, what we do is that we pick a subset of feature from here. Okay. So let's say one subset that I pick is, let's say, F10, F98, F15, let's say F1. Okay. This is a subset, small subset, let's say, that we pick. So if I pick a subset, and when what is the question that we ask here? The question that we ask here is whether my Fi is less than equal to theta, right? This is the question that we ask. Now, instead of looking at all these features and checking for which set of features it is giving you the answer yes, and for which of the features it is giving you the answer no, instead of doing that, you are going to, so we will not do this. What we will do is we will use this subset of the feature, and from this subset of features, we will ask this question. So we'll ask whether F10 is less than equal to theta, whether F98 is less than equal to theta. So we'll, from these four features now, we'll pick the most appropriate feature. Like we'll pick that feature which has some maximum information gain, right? So suppose we get some, let's say, that is satisfied by, let's say, some feature F15. So let's say my feature F15 has the maximum information gain. So for the first node, we have my F15 less than equal to theta, let's say. Now, again, you will ask different question again right here. So after this, again, you will ask two questions, right? I mean, if yes, then again another question. If no, again another question. You will have something like this. So again, you will have to decide some another question. So for let's say for there for f some fj less than equal to theta. Now again, you will not go to this whole set of features and check. What you will do is, again, you will take a subset of feature. So let's say this time I took a subset of, for deciding the question for here, which feature, for deciding the feature for this node, we are going to, let's say, take some other, another subset. And let's say this subset is some F2, F77, F9, F50. Okay. Now we will look at this set of feature and we will ask the same question, right? And we will see which among these four features has the maximum information gain, and we'll pick that feature for our decision tree. So this is how we can design, we can do this feature bagging technique, right? So and this we will do for all the trees. So all these data set D1, D2 up to DM, right? So if we do this, so if we bag the feature, so every tree, instead of using all the features, they will use a subset of feature, right? And since they will use a subset of features, and you can get, and it's not that all the trees are going to use the same set of features. So it will be different, right? So if we do this feature bagging, this will make sure that uh, the HIs that we get, they are as uncorrelated as possible. So this is the idea of doing the feature bagging. And the ideal, and the rule of thumb is that the number of features that you should use in feature bagging is some under root of D. So let's say if you had F1, let's say you have 9 features. So in feature bagging, so pick the subset of the feature. You will let's say you pick a subset of 3 and we will decide. So this is the idea. Is it okay? Is it clear? So random forest is nothing but your feature bagging in basically. You're doing the bootstrapping, you're bagging your trees, and then you're also bagging the features. And you're bagging the features to make sure that the classifiers that you get are as uncorrelated as possible. And and that will make sure that the variance reduction is maximum. Okay. Hope this is fine. All right. So the next and the last topic for this week is boosting. So in boosting, we are going to learn an algorithm which we call it as AdaBoost. And AdaBoost, so this Ada means here adaptive boost. Here, this is adaptive basically. In short, we are calling it as AdaBoost. So where in bagging we were doing two steps, one is bootstrapping, another was aggregation. What we will do, like why boosting is important is because, I mean, even in bagging, we were trying to convert this weak learner to the strong learner. So even boosting does the same job, like it converts the weak learner to the strong learner. But where bagging we were doing only for the overfit model, this boosting can be used even for the underfit model. Okay. So that is why this technique is very powerful, because when you're talking about an underfit model, so if we take the example of decision tree itself, so what can happen is, like, maybe if let's say an ideal decision tree, if let's say if it asks some 10 to 11 questions, maybe in when we are saying that it is an underfit model, maybe it is just asking 1 to 2 questions, one to two level of question it is asking, and that's all. So we will like what we will do, and this will not take much time, right? This is not very this is kind of a simpler model. Overfit model, like more like simple models. So this will be good, like even for the underfit model, we can convert these to the strong learners. So, okay. So now, if we take the decision tree example, so what here we will call it as not the decision tree, we'll call it as decision stump. We call it as decision stump because we are only going to ask some 1 to 2 questions, and that's all, like 1 to 2 level of nodes we will have. Okay. So in AdaBoost, what do we do is, now this is an iterative technique. So suppose you have a data set, x1, y1, x2, y2, xn, yn. Okay. And in a boosting algorithm, in this AdaBoost algorithm, what we are going to do is, since it is an iterative technique, so we will initialize let's say d naught I. This is 0 for zeroth iteration. And D here is for the distribution. Okay, this is denoting the distribution. So we are initializing each of the data point, the distribution for each of the data point uniformly as 1 by n. So what does it mean? What it means is, like, let's say this is more like the uniform distribution. So every data point has the same probability of coming in for the bags that we are going to make, basically. So in the starting, we are going to we are going to say that the distribution, the way this data points will come in for our bag that we choose is going to be uniformly distributed. So since there are n data point, every data point will have the same weightage of coming in the bag. Okay. So this is the first technique, the first step, that is initialization. Now next, what will happen is, like, once you get the bag, so and now the way you have gotten this bag, let's say the bag that you got, in this bag, the data points will come again from here, but now it has some probability distribution to it, right? because now we are also assuming that this is not random. I mean, these points are given the equal importance, I mean, equal weightage, you can say. Each have the same probability of coming into this bag. All right. So this is the initialization. Now for now for t is equal to 1, 2, so on till capital T, like for these number of iterations, what you're going to like once you have this bag, okay, now again on this bag what you're going to do is again you will um, now where in bagging when we're doing the bagging we were overfitting the model. Now here we will underfit the model. So since we are talking about decision tree, let's say we are underfitting this tree, and from there we get some HT. We'll get some HT. For at every step we get some HT, where HT will vary from RD to my plus minus one, right? Because the classification. Now, for these labels, I mean, at each iteration, I am going to get some classifier HT, correct? And the way we are going to get those classified by underfitting the decision tree, and those are my weak learners. But let's say I get some HT, and this HT, I mean, this decision tree is like for any new uh, test data set. Let's say if this decision tree is going to classify uh, some data set to be some if some data set are able to get classified correctly and some are not able to get classified correctly, then what the way we are giving the weights to these data point in the second step when we do the bagging, when we are taking the data set, basically what we will do is the data point which did not get correctly classified, we will give those data point more weightage when we are creating this data set. Okay. So, like if let's say the data points which were correctly classified at the Th step and the Th iteration, now those data set will be given less importance or less weight as compared to the data set which were not correctly classified at this iteration. And the way we give those weights, so I mean the distribution for now the distribution for the data points, the way it is going to be is, let's say, some d tilde d plus 1 of I data point. This is going to be, so this is t plus 1 to show the t plus 1 iteration. This is the dti and times e to the power alpha t. If your ht xi is not equal to yi. So if your classifier is not going to correctly classify your data point, then those data points you are going to multiply by this term, which is e to the power alpha t. Okay. And for the cases where it correctly classified, right, where ht of xi was equal to yi, then there again you will multiply the data point with some term, but this time it is e to the power minus alpha t. So from here you can see that like the data points which were incorrectly classified, they are given more, I mean, the probability of choosing those data point now is higher. Okay. So because you are multiplying it by e to the power alpha t and it is increasing function. And the probability now for, I mean, the data points which were correctly classified, the probabilities of choosing those data points in the next round is now lesser. Okay. So this will help you, like this will help us in uh, getting, I mean, getting more data points to be like correctly classified in a sense. So, but one more thing that these, if you add these two, since this DTI is a distribution, they should ideally add up to one, but they are not adding up to one, right? They're not adding up to one. So what we can do is my dt plus 1 of I should be equal to my d tilde t plus 1 I divided by, you sum this dti, right? Some j. And basically, you're normalizing this. So once you normalize this, all the probabilities for all these data points, the probabilities now will add up to 1. That is the idea. And again, at the end, like at the end of TH iteration, you will get some H1, H2. Again, you will get HT. You will have those C classifiers. And the final classifier, the aggregated classifier that you will get at the TH step of the iteration is going to be again sine of your sum over HTX, where T is varying from 1 to N. T is varying from 1 to capital T. But now you will multiply this HTX with uh, this weight alpha T. So now in this case, in boosting, this is the final classifier when you're creating. This is the weighted. Now this is not just the average. This is the weighted average of your classifier, and these weights you give by this alpha T. And this alpha T basically, like this is from like some proof has been given. I mean, not in the lecture, but in general, if you look at the proof, what you will get is this alpha T is ln of 1 minus error of HT divided by error of HT. Okay. So this is what you get the final classifier as in boosting. All right. So yeah, that was all about bagging and boosting. Okay. So there are few more things that has been given in the lecture for the boosting, but those are not really we are looking into detail. So we have skipped that part. If you are watching through the lectures, please go through it. We have not done that part over here. Okay. So that was all about week 11. Um, Maybe if you have any question, you can ask. We'll stop here. All right then. Let's close for today now, and we'll meet again for week 12. Okay.
Thank you so much, ma'am.
Yeah. Thank you all. Good night.
Thank you, ma'am.